Good afternoon and welcome to the third presentation of the Global EV Charging webinar event on EV charging best practices and power quality. Tim Slange and I will be hosting these webinars, and during each webinar, one of us will be the host and the other one will be monitoring the questions log, and we'll select questions to be answered after each presentation. You can find the question box in the GoToWebinar tool. Please use that box and not the chat box for any questions. It is still possible to register for the other webinars via our website, and all the webinars will also be recorded and uploaded to our YouTube channel. So if you've skipped any of the webinars, keep an eye on our ElaadNL YouTube channel and please subscribe to receive notifications. This event has been made possible with support of the Progresses project. This project focuses on creating a new generation of efficient charging infrastructure. And, well, of course, our event is also focusing on this. And now, without further ado, it is my pleasure to announce our next speakers. Karima Boukir, Senior Consultant on Electric Mobility from Enedis, and Kevin Lorenzo, Research Engineer at EDF R&D, and they will present 6 recommendations they've set up together with us to share awareness of power quality impact and improve e-mobility grid integration for EV stakeholders. But first, a few words from Baarten de Brij, our Chief International Officer, and Pierre Faivre, Chief Strategy and Business Development Officer from Enedis, about the cooperation between ElaadNL and Enedis.
Yes, thank you very much, Thijs, and compliments, first of all, on organizing this event again, 3rd year on a row, and a 3rd year of collaboration also with Enedis. Started with the importance of interoperability between EV drivers who want to go on a summer vacation from the Netherlands towards France, or a city trip from Paris to Amsterdam. But apart from interoperability, also other aspects of EV charging are very, very important. And this is where Elaad and Enedis found each other. Today, Karima and her team will present us something about power quality. It is the result of intense and good, successful collaboration between Elaad and Enedis, the test labs we have in Arnhem and in Paris. And I'm looking forward to see this results. Now, I would like to give the floor to my colleague, Pierre Faivre, who will also introduce this successful collaboration and the presentation of Karima and Kevin. Thank you.
Hi everyone, I'm Pierre Faivre, Head of Electric Mobility at Enedis, the French DSO, and I'm really delighted to be with you today and to have the opportunity to open this power quality webinar session together with Bart from Elaad. I think it's really important we can organize such events, gathering experts and stakeholders that are working to make the grid integration of electric mobility a success. I think there is no question anymore about the takeoff of these markets everywhere in Europe, and that's good news. We can see more and more electric vehicles on our roads. That's just what we need to do. Of course, as a DSO, we are fully committed to decarbonize transport, one of the most emitting sectors of the economy. And we work in order to anticipate, because at the end, every charging point will have to be connected to the distribution network. And I think the collaboration between Elaad and Enedis is very key and very important. I also like the fact that it's not only working together and doing let's say researches and things like that, but we have already tangible results and that we can share with you today. As one of these outcomes, there is a paper, because we worked in 2020 together with Elaad and Enedis on let's say power disturbance on the grid. And on this paper, we share guidelines and recommendations in terms of power quality. I'm sure that will be of interest for you. And also, I think this is the opportunity for you to connect to each other and to share your expertise and experiences between you. So that's what I think, and I hope you will enjoy this power quality seminar. Bye bye.
Thank you, Taj, and Bart and Pierre for introducing this session. We are going here to present you kind of a brochure where we gathered 6 recommendations resulted from results and observations through labs testing with different EVs in France, in the Paris area, and in the Netherlands, in Arnhem. Why we are interested in focusing on EV and power disturbances from EVs. Actually, this is a new use. We are not up to the full deployment yet, so we expect maybe even rare some malfunctions due to unknown scenarios of charging, for instance. And because EV also has power electronics, which will be added to all the uses on our network. Also, EVs have a specific thing as a use because it moves. It means they will change the plugs from home plugging, home charging for slow charging when they park at home, from public charging on the street, work charging at the office, while they travel through the motorways, and fast charging. So all these configurations, and also self-consumption as well, we think it is a special use that is interacting with the network in different scenarios and in different situations. For instance, also in hubs, they might cross other EVs while charging. And also, there are different car manufacturers. We believe there is awareness of power quality to share within all EV stakeholders. And also, there is a specificity of EVs as they have storage. We think it is a good flexible mean on the network. Therefore, smart charging has a big value to relax, I would say, to relieve stress on the network, either on local or on the bulk power system. So in the future, we think there should be something that we need to anticipate to avoid all these, I would say, bad surprises. That is why we, with ELAAD, we worked from our sides differently for many years, but in 2019, we gathered all the testing things we have done in this topic to compare and try to find some similarities and some complementarities. We will focus in this presentation on 2 power disturbances, harmonic distortions from 0 to 2 kilohertz, and supraharmonic distortions from 2 to 150 kilohertz. So this is the test labs, one in Paris area, led by for Enedis testing on their network, but in the EDF R&D premises. You can see Kevin on the bottom left, and on the right side you have the ELAAD test lab, and I think is staged on the the bottom right. Yeah. Now, let us say a bit of why we are here today and what we wanted to share with you. Actually, we published these 6 power quality recommendations in this brochure of 4 pages, where we gathered the 6 recommendations, one about raising awareness among the stakeholders of EVs, car manufacturers, charging stations manufacturers, 2 about smart charging standardization for harmonic emissions and supraharmonic emissions. Another one about what is a good assessment of power quality of EV charging in a laboratory. The other one is to put labels on power quality proven and smart charging ready. Also, there is another thing we would like to highlight is about adaptation of charging power to voltage levels. Okay, now I will hand over to Kevin to present in more details why and the reason of each of these recommendations. Thank you.
Thanks, Karima, and good afternoon, everybody. Okay, so the first observation from test results that we wanted to share is that there is actually a significant effect of smart charging, here meaning the power modulation during charging, on the harmonic emissions from EV chargers. So on the graph here on the slide, you can see the current total harmonic distortion of 4 different EV chargers as a function of the charging current, which was during the test modulated by a smart wall box. Okay, so what we observe is that, so first, the harmonic emissions, they are very dependent on the charging speed, which actually represent the different operating point of the charger. Then that this behavior actually is very different from one vehicle to another. Some are less sensitive than others to the operating points, and that some vehicles have kind of optimized operating points in terms of power quality. We can see, for example, on the black curve, that the harmonic emission are quite low when the vehicle is charging as 15 amps, for example, and it's much higher, the THG is much higher as 16 amp, which is probably explained by a kind of a modular conception of the charger itself. Okay, so there is this significant effect, but still in the IEC standards, which are defining harmonic current limits for the electrical equipment such as EVs, there is only one operating point that is used for compliance testing. So the recommendation we would have for that in the next slide would be to define a new category of controllable loads, which would actually include EVs, but not only, in standards which are limiting harmonics. And for this category, in addition to the already existing and already defined harmonic limits, some new limits would be adapted, and there would be limits at different operating points that could be set, for example, as a percentage of the current instead of only one testing point. And this would, of course, require to adapt the standard compliance tests in order to address several operating points. Okay, so the second observation we wanted to share on the next slide is actually quite similar, but it concerns the supraharmonic domain this time. So this graph that we can see, it shows the supraharmonic emissions from an EV charger as a function of time. So here, yellow means that there is a significant emission, and the deep blue, it means that there are very low emissions at the frequencies, at these frequencies. So in the middle of the graph, there is a shifting from an uncontrolled charging, so charging at rated power of a station, to controlled charging at modulated power, what we call here smart charging. And what we can observe is that first, the supraharmonic distortion is very dependent to the charging power, actually, since the behavior is very different between the two situations. And also, in this specific case for this EV, there is a large band distortion that is appearing around 45 to 50 kilohertz. Okay, so about supraharmonics, it is well known that they can have effects on the grid, since they can cause overheating of components or even malfunctioning of electric or grid components. And also for countries such as in France, where PLC communications are used for smart metering, well, it is essential to ensure that these distortions do not disturb the communications of the smart metering system. But still, even though we observe this effect, at the moment there is not much that is known about the propagation of these emissions, and there is no formal standard for emission immunity or testing that has been defined. So the recommendation we would have for that would be to first to, as we say, to continue to carry out some research activities in this area, in order first to better understand how the supraharmonic currents they propagate through the grid, and also to apprehend the to comprehend the effect they have on grid components or on other electronic devices. And this would be mainly fed by testing activities and measurements, lab measurements. And then, as the standards in this domain are not completely available yet, or are not fully defined, the idea would be there again to suggest a category of controllable loads in the future standards that will limit supraharmonics on grids. Nice. So another observation that we had on the next slide. So we actually specifically discussed about harmonics and supraharmonics emissions of EV chargers. But actually, in order to have a kind of more complete characterization of an EV charger, there are a lot of tests that can be done. And actually, there are a lot of tests because there are a lot of parameters of EV charging that impact the way the charger behaves. So first, for example, the grid conditions, the voltage level, the distortions that are already present on the grid, or the impedance of the grid, they have an effect on the way the charger behaves. The charging mode as well is very important, and especially, for example, for DC charging, which is called the mode 4 of charging. The sensitive equipment is actually in the station, since the conversion is in the station and it's not embedded into the vehicle. Another thing we already discussed about that on harmonic and supraharmonic behavior is the power modulation that has a real impact, but also the closed environment of the charging of the EV that is charging is very important. For example, whether the IV is isolated and tested alone, or if the other vehicles are charging at the same time in the closed environment, it really can have an effect on the behavior of the EV that is charging. So with variations of all these parameters, a lot of tests can help to have a characterization and a good understanding of each EV. But yet, at this moment, there is no standard testing procedure for an EV charger characterization, nor clear KPIs for that. So the recommendation for that would be to define a standard testing procedure to characterize EV chargers. And this would include at least some tests in order to assess the efficiency of smart charging of each EV. Then some measurements of harmonics and supraharmonics emissions for most of the operating points of the charger. And last but not least, since it's quite essential, to test the sensitivity of EV chargers to harmonics or supraharmonics already present on the grid. And for each of these tests or measurements, some clear KPIs or targets related to the test are of course necessary as well to know if the test is passed somehow. Okay. Next, actually, one of the things we observed is that most of current legislation concerning road vehicles, they relate only to vehicle safety or driving characteristics, and there is not much consideration towards the factors directly related to EVs or their charging. So first, on the capacity to control charging, we actually observed that some EVs do not have an efficient smart charging. We can, for example, observe on the left curve that some vehicles, they have some operating points that are not reachable, and so the charging stops for some of the operating point of the charger. And then also on the emissions and immunity of vehicles, immunity to distortions, we observe that some EVs are very sensitive to grid distortions, and sometimes even some vehicles, they stop charging while there are some distortions on the grid, but still the grid conditions are compliant to the grid codes, for example. So this is what we observed, and what we would suggest as a recommendation for that, which appear on the next slide, is that some kind of labels, they could be defined, and they are related to the standard testing procedure that we discussed before. And the first one could be a poor quality proven kind of label, in order to ensure the good harmonic and supraharmonic behavior of EV chargers. And the second one would be more directly related to smart charging, and it would be a kind of smart charging ready label, in order to ensure three main things for smart charging. First, that the EV time responsiveness to station instructions is okay and is good enough to do smart charging efficiently. Secondly, that the EV capability to follow charging speeds or charging power transmitted by charging station is okay and is good enough. And third, it's also important to ensure the ability to maintain charging efficiency when the charging is done at low speeds or at low power. Okay. So this was the one of the main observation and recommendations, and we have a last observation we wanted to share. Actually, on the contrary to the last observation, it was also observed that some vehicles, they continue charging, or even they increase their current intake when the grid conditions are not satisfying anymore. For example, when the voltage drops, which is not really a good behavior for any electronic equipment. So here is, for example, an EV charger, a specific one, which continues charging even at an increased current, while there is a voltage sag to only 100 volts on the grid. And where, of course, it should actually stop in order, the charger should stop in order to preserve its components, but also the grid. Okay, and so for this was the observation and the recommendation for that, in order to avoid that EV continuous charging during voltage drops, would be to make some evolution in the standards and to address some threshold values. And for example, the following standard would be recommended. A first one where the charging stations or the EV should measure the voltage and reduce the charging speed if there is a drop of the voltage at a specified value. Also to respect the threshold values of voltage limits that are defined in the grid codes. For example, in the standard IEC 50 or 160, there are some limits for voltage drops that are defined, and it should be good to respect them. And the last one, so the vehicle should be able to detect malfunction or the station itself in the energy supply and stop charging if there's a sudden voltage drop, for example.
Okay. It's okay, Kevin?
Yes.
Thank you, Kevin. Thank you so much of being so respectful of the time we let. Yeah, it was about 15 minutes, and it was fully respected. Thank you. And yeah, as I mentioned from the beginning, we have one major rule, one major recommendation, which is about raising awareness on power quality issues among e-mobility players. Yeah, we need really to increase the education of these new players with electricity and let them know that there is something which may occur and they need further maybe standards to apply, or maybe some trainings as well. And we think also there are some bases about electricity that maybe anyone, any citizen may have to, I would say, have in mind. And for this matter, both Enedis, EDF, and ELAD produced these two movies that are very simple to understand. And these movies will be projected after this session, after the questions. Thank you for your attention, and you can contact us. There are our emails at the bottom of this slide. Thank you.
Oh, thank you, Karima, for these final words. It's now time for the questions. I do have a question myself. The paper where this presentation is based on, will it also be able to download it from the Enedis website somewhere?
I would say Enedis website is huge. In the brochure, we put some videos, the one which will be presented right now. Most of the papers are in CIRAD, actually. They are published in CIRAD. Yeah. So we used to publish all our knowledge and research in this kind of conference.
Yeah. We will also upload the recommendation document on the ElaadNL website for people to download it if they just want to read the 6 recommendations we have.
Okay.
So that's and another question. Looking at all the recommendations we have, which one do you consider to be like the holy grail, the most important one?
To me, is the power quality labels. To me, okay. is the result, because as a e-driver, I would ask for that.
Yeah. Now let me see. We've got a couple of questions. We have about 10 minutes for the questions remaining, and then we will start the 2 videos. So let's see. We have a question from Sharmista and from Enedis, who is actually also presenting tomorrow. And same kind of question we had from Rudy de Winter, and they're both on supraharmonics and if there are any customer complaints you've received as a DSO about EV charging and, well, power quality issues.
Okay, so actually some direct,
some direct
customer complaints
yeah.
about supraharmonics. They are not always formulated this way. So there are some complaints about, for example, charging stations which are not working quite well. And then the thing is to understand if it's coming from the stations, if it's coming from grid events, or if it's coming from the vehicles that are emitting some distortions. And it's always a matter of having some observation possibilities on site. So whenever there are some malfunctions of charging stations or charging environments for EVs, for example, we are able with our test and measuring equipment to go on site and to measure the different indicators of power quality, and then to try to understand if it's really coming from harmonics, supraharmonics, or coming from somewhere else. So sometimes it's coming from supraharmonics and also interactions between equipments with supraharmonics, which go from one equipment to another, and sometimes the interactions and the cohabitation between equipment is not quite well. But of course the customer challenge is never about supraharmonics, for example. It's about something that is working not quite well on the grid.
Yeah, it shows that it's not that easy indeed. You really need to measure and research each of these complaints to really find out what's going on.
But I agree with your colleague, Tej. It happens that some cars that are, I would say, new brands on our roads, for some chargers, they refused to charge. So we had it in our own building. So that is why. So, but we find each time a solution from our own colleagues. So it's funny, but yeah.
Yeah. So that also shows, like, okay, if there's a new vehicle, test and see how it behaves, and prepare your infrastructure to also prepare the infrastructure, but also the EVs to better integrate with each other.
It's not even infrastructure. It may be a little thing that is in the car park, embedded in the private network. You know, the little something that. In this case, for security reasons, there was something that was functioning to maintain all the lights on, and it was emitting a bit. So a little thing, but it can effectively. I agree with your colleague. It's not supraharmonic, but a little thing that may avoid blocking charging. But we learn each day.
Excellent. I also have a question from Cyan. Well, first of all, he says it's a great presentation and it's very insightful. So there are some compliments for you. He has a question: do you see different power quality behavior if multiple electric vehicles are charging at the same time?
Yeah, definitely. Actually, when several vehicles of the same model are charging at the same time on the same infrastructure, there are some phenomena that can be observed, such as intermodulations in the supraharmonic. So one of the graphs in the slides, it was showing that some intermodulation phenomena, which is the resulting from some slight differences on the way the charging is controlled into the charger by a kind of PWM modulation. So this kind of thing we observed. Also, when two different vehicles or several vehicles or different models are charging at the same time on the same infrastructure, they influence themselves, which means the behavior of the first connected is a bit different when the second one connects to the grid at the same time, since there are some interactions between the vehicles and some distortions that are passing through, and especially for supraharmonics. Actually, for harmonics, the behavior of each vehicle is not really dependent on the environment in terms of what our equipments are connected. But for supraharmonics, it's very much dependent on the environment and the other equipments that are operated at the same time. Sorry.
Okay, excellent. Thank you. Let's see. Well, another question. What are your own next steps? How are you going to attribute yourself to well, help achieve with the recommendations, to achieve the recommendations?
Okay, so for that, first, well, indeed, all of these recommendations that are they are mainly long-term recommendations. So these are recommendations in order to solve the problems as a whole for the long term. Of course, when there are some situations where charging is not possible because of poor quality phenomena of any kind, there are some short-term solutions, and then we can act with filters and everything. Well, then in order to go to this long-term approach, the first, well, the next step would be to first continue to do some kind of systematic measurements on the vehicles which are the more likely to develop and to have a big shares of the market of EVs. But this is not a sustainable approach for the long term. So then the other next step is to try to work with our colleagues which are involved into all standardization bodies that are dealing with poor quality, in order to give them some of our results already obtained, and try to give them some guidance in order to feed the standardization bodies with this kind of recommendations. And so the internal next steps are mainly these ones: continue testing, but also trying to feed standardization bodies thanks to our colleagues that are already involved in the groups.
Okay, yeah, excellent. That's a great approach. And to add to this about well, the testing of electric vehicles at this moment. We at ElaadNL, we have a test lab, of course, to test electric vehicles and DC chargers on things like smart charging, power quality, and our test lab is open for, well, all manufacturers to contact us and to reserve a time slot for these tests, and to, well, get advice on how their vehicle behaves and how it can be improved. So for all attendees, if you have some, well, hardware you would like to have tested, please contact ElaadNL, and we can help you out there. So it's 10 minutes past half, so we would like to start our nice animations about power quality. So this will be the end of the presentation now. For everybody, I'll enjoy the videos. And Karima, Kevin, well, thank you for your interesting presentation, and see you around.
Yeah.
Thank you. Goodbye. See you.
L'électricité, vous savez ce que c'est? C'est un flux d'électrons qui transporte de l'énergie d'un point à un autre et qui peut faire briller, chauffer ou tourner toutes sortes de machines. Le premier à avoir produit assez d'électricité pour éclairer une ville comme New York ou Paris, c'est Thomas Edison. Il utilisait de gigantesques dynamos et son courant circulait de manière continue. Puis Nikola Tesla est entré en scène grâce à ses alternateurs et à son courant alternatif. On a réussi à envoyer l'électricité sur de plus longues distances, facilitant ainsi son transport du producteur au consommateur. Au début, tout se passait très bien et la fée électricité multipliait les petits miracles dans les foyers. Mais l'apparition du confort moderne a changé la donne. Les réfrigérateurs, les aspirateurs, les machines à laver. Bref, tout ce qui avait un moteur a créé un déphasage entre la tension et le courant, provoquant des chutes de tension sur le réseau. Puis les matériels électroniques tels que les téléviseurs ont déformé l'onde originale, induisant des courants harmoniques qui modifient la forme d'onde de la tension et qui peuvent accentuer des phénomènes de résonance dangereux pour les équipements électriques. Parfaitement propre à la sortie des sites de production, le signal électrique s'est ainsi détérioré au fil des usages. Pour en protéger la qualité, il a fallu installer des équipements nouveaux à proximité des moteurs et placer des filtres dans les appareils les plus polluants. Et aujourd'hui, me direz-vous, eh bien aujourd'hui, les problèmes techniques n'ont pas disparu. Ils s'annoncent même comme de vrais défis. Avec les lampes basse consommation et les LED, les ordinateurs individuels ou les téléphones portables, dont les chargeurs se font toujours plus petits, la pollution s'est déplacée vers des fréquences de plus en plus hautes qui gênent le bon fonctionnement de l'électronique moderne. Et puis les appareils actuels ne se comportent plus du tout comme ceux d'avant. Combinés à des équipements plus puissants, comme les pompes à chaleur ou les véhicules électriques, et associés aux panneaux photovoltaïques qui produisent leur propre électricité, ils modifient désormais le déphasage du signal et complexifient la conduite du réseau, altérant ainsi la qualité de l'électricité. Toutes ces perturbations nouvelles appellent à trouver des solutions innovantes, et c'est à cela que travaillent les équipes de la recherche et du développement du groupe EDF. En l'auscultant sans cesse pour mesurer et diagnostiquer les pannes et les perturbations, elle s'intéresse de très près à l'état de santé du réseau électrique. Et tandis qu'elle s'active dans leur laboratoire à inventer et à tester de nouvelles solutions, elle s'attelle aussi à éditer les normes de demain qui assureront une bonne compatibilité entre le réseau et les matériels électriques. Enfin, les équipes d'EDF travaillent à construire le réseau de demain pour qu'avec plus d'intelligence et de flexibilité, il soit possible de s'adapter rapidement et efficacement aux sollicitations qui s'annoncent. Car assurer la qualité de l'électricité, c'est anticiper dès aujourd'hui les usages de demain.
Do you know that good power can turn bad? And that this bad power quality can lead to things like whistling induction hobs, to charging problems, and to device malfunction. So, what causes bad power? It's all to do with the converter. Many devices operate on alternating current, but we're adding more and more rechargeable devices that run on direct current. And for these, you need a converter. That's also true for an electric vehicle. The charger's current changes direction 50 times per second. By switching extremely quickly, the converter ensures that the current flows in one direction. But this switching, especially if not filtered correctly, can cause so-called supraharmonic disturbances. And as a car converts a relatively large amount of power, this can lead to serious disturbances. These can be so large, they can disrupt the power quality in your home, and even that of the grid. The more energy that is badly converted, the greater the disturbance. Good power can turn bad. The consequences? Unwanted heating of parts, extra wear and tear, device malfunction, and eventually breakdown. And the good news? It's quite easy to stop this from happening. Use good converters and filters. Set standards and test them, starting with electric cars. ElaadNL researches and tests smart charging on behalf of the Dutch grid operators.